Hey everyone, and welcome. So let's talk about something really fundamental to, well, everything. How does energy actually move through nature? We're going to dive into how it's all connected, and you'll see how pulling out just one tiny thread can make the whole tapestry unravel in ways you would never expect.
Think about that for a second. How can removing one single species, an animal, actually cause a river to change its course? It sounds crazy, right? Impossible even. But that is the exact mystery we are going to solve today. Stick with me, because by the end of this, you're not only going to have the answer, you'll see the powerful hidden forces that make it all happen.
All right, let's start with something we probably all remember from science class, right? The good old food chain. It's really the most straightforward way to picture how energy moves around in nature.
So what is it really? At its heart, a food chain is just a super simple diagram of who eats whom. That's it. It just draws one straight line showing how energy gets passed from one creature to the next as you go up the different what scientists call trophic levels, basically the feeding levels. Okay, so here's that classic example we all know. You've got the sun kicking things off, providing the juice for the grass, our producer. Then a grasshopper comes along and eats the grass. A frog eats the grasshopper, a snake eats the frog, and finally, the eagle, our apex predator, swoops in and eats the snake. It's just so clean, right? A perfect step-by-step story. But, and this is a big but, nature is almost never this simple.
And here's the problem. Real life is messy. A snake doesn't only eat frogs, right? An eagle eats way more than just snakes. And that frog? It's munching on all sorts of bugs, not just grasshoppers. So this neat one-to-one model, well, it kind of falls apart the second you start looking at what actually happens out there.
So if a simple straight line doesn't cut it, what does? Well, this is where we need a bigger, better model, one that actually captures all that beautiful, chaotic reality. And that, my friends, is the food web. Yeah, so instead of just one single path, a food web is more like a giant map of all the interconnected paths. The highway system analogy is perfect. It's not one single road, it's a whole network with tons of on-ramps, off-ramps, and intersections that connect everybody in the community. And this really shows you the difference, side by side. A food chain, it's brittle. If all the frogs vanish, that snake is in big trouble. But in a food web, well, the snake probably has other things it can eat. It's got options, and that's the key. This web-like view shows us that ecosystems are way more stable and adaptable for one simple reason. There's almost always a plan B. The secret sauce here is a concept called redundancy, and it's just what it sounds like. If you have several different predators all hunting, say, rabbits, the system has a built-in safety net. If one of those predators disappears, it's okay. Others are still on the job. If one food source dries up, the energy just finds another way to flow. That flexibility is exactly what makes the whole system so strong.
But what if there isn't a backup? What happens when one species is so important, so unique, that no one else can do its job? Well, that's when we get to something called the keystone effect.
You know the keystone in a Roman arch? That wedge-shaped stone right at the very top? It isn't the biggest stone, not by a long shot, but if you pulled that one stone out, the whole arch comes crashing down. A keystone species is exactly like that. It might not be the most common animal out there, but its presence is absolutely critical to holding the whole system together.
This whole idea comes from an ecologist named Robert Payne, back in the 1960s. And he wasn't just some guy with a theory. No, he wanted to prove it. So he designed this really bold, surprisingly simple experiment out on the rocky coast of Washington.
What he did was, well, it was incredibly direct. He just went out to this tidal area and physically removed every single purple sea star he could find. That's it. See, these sea stars love to eat mussels, and Payne had one simple, burning question. What happens to this whole place if you just get rid of its main predator? The results were, wow. They were fast and they were dramatic. With no sea stars to eat them, the mussel population just went crazy. They completely blanketed the rocks, pushing out everything else, the algae, the snails, everything. In just 1 year, the number of species in that area was cut in half. Payne had found his proof. The sea star was, without a doubt, a keystone species.
And this crazy ripple effect that Payne saw? It has a name. It's called a trophic cascade. It's that chain reaction that gets set off when you pull out a top predator and the effects just tumble down and down and down through every level of the food web, changing everything. And this brings us right back to that question I asked at the very beginning. Because the most famous, most powerful example of a trophic cascade comes from Yellowstone National Park.
And it's all about one animal, the gray wolf.
Okay, just look at this. It lays out the whole story. In the before wolves column, you can see what happened. The elk population went through the roof, and they ate everything. The willow and aspen trees just got decimated. The beavers, who need those trees, vanished. And without the tree roots holding the soil together, the riverbanks started eroding, and the rivers got wider and messier. But then, look what happens after the wolves come back. The whole thing flips. The wolves keep the elk in check, which lets the trees grow back. With trees, the beavers come back and build dams. And with all that new vegetation along the rivers, the banks stabilize, the erosion stops, and the rivers actually narrow and find their proper course. So, the answer to our crazy question? Yes, absolutely yes. One animal really did change the course of the rivers.
So, the Yellowstone story is just this unbelievable real-world example of how this all works. But what's the big takeaway? Why does it even matter if we see nature as a chain or a web?
Well, it's about a huge shift in thinking. It's about moving away from seeing nature as this simple, linear, almost mechanical thing, to seeing it for what it is, a living, breathing, incredibly complex network. Energy isn't just taking one road, it's flowing and shifting through this massive web of relationships.
And thinking this way has massive, real-world consequences. For conservation biologists, it means you don't just protect one species in a vacuum. You have to protect the critical relationships between them. For wildlife managers, it helps them see the ripple effects of their decisions before they make them. And for people trying to restore a damaged ecosystem, it gives them a blueprint. Focus on rebuilding those key connections to get the whole network buzzing again.
At the end of the day, that's really what it's all about. When we look at these food webs, we're not just playing a game of who eats whom. We're starting to understand the fundamental rules for how energy organizes life itself. It's just a much deeper, more connected way of seeing our world. So, I'll leave you with this to think about. If a single species can literally change the shape of a landscape, what are the keystone connections in our worlds, in our cities, in our economies, even in our own social circles? What are those absolutely critical links that we might be taking for granted? And what would happen if one day they were just gone?